Greetings everyone. This is the lecture for section 3.1, Graphing Equations. What we'll be covering in this lecture are the introduction to the rectangular coordinate system, which also goes by the name Cartesian coordinate system. The names are interchangeable, and the parts that put those together. You'll have an x-axis, the horizontal axis, the y-axis, which is the vertical axis. They intersect at a point called the origin and divide the plane into 4 quadrants: 1, 2, 3, and 4. We'll also be looking at linear equations in 2 variables. Linear equations means that the graph will be a line, something like this. And the form of the equations we look at in this section, you have the 2 variables, x and y, and the form will be coefficient a times x plus a coefficient b times y equals c. This is called the standard form, and that holds provided that at least a or b is not 0. Also, we will bump into a couple of terms. The old-fashioned way of saying x is abscissa. The old-fashioned way of saying y is ordinate. Graphing points in the plane simply involves using the x-coordinate as a horizontal displacement from the origin, and then the y-coordinate as the vertical displacement. So starting at the origin with point A, 2 in the positive direction, that's what the x says, displaced from the origin, and then down 3. You start at the origin and then displace in both directions. So that's the point A. That happens to be in quadrant 4. Then we have 0b. You're starting at the origin, you have a horizontal displacement of 0, so you don't move horizontally. And then you go up pi, which is a shade more than 3. Pi would be approximately right there. So that would be the point 0 pi. That's on the y-axis. Then you have the point C. The negative 2 displacement means 2 to the left from the origin, then down square root of 5. Square root of 5 is a tad more than 2, so this will be a tad below negative 2, about right there. And that will be the point C. That's in quadrant 3. If you notice, we customarily use Roman numerals for the quadrants. It reduces the temptation to ever want to calculate with them. Next, we ask ourselves, could an order pair be a solution to an equation? Solution to an equation means that you make the equation true. So in other words, if you take 1 and put it in for x, and you take 6 and put it in for y, do you have a true statement? This equation, if we make that substitution, 6 for y, does that equal 3 times the absolute value of 1 minus 1? Well, 1 minus 1 is 0. So you're going to have 3 times the absolute value of 0. And that's going to be 3 times 0. That does not equal 6. So therefore 1 comma 6 is not a solution. Notice that the solution to an equation with 2 variables has to have a value for each variable. There has to be an x and a y. Writing them as a ordered pair is a compact way of saying this one's x, this one's y. On the other hand, if we look at the equation in part B, we have the same y, then we have the absolute value of -1 minus 1. Well, that's going to be the absolute value of -2 being multiplied by a 3. And might that be equal to 6? Well, absolute value of -2 is +2. So that is indeed true. Therefore, -1, 6 is a solution. Determine whether the equation is linear, then graph the equation by plotting ordered pairs. So there are two things to do here. First, the absolute ironclad way to make sure an equation is linear is to write it into standard form. If you can write it into standard form, it is linear. So that would mean getting the x and y terms to the same side. I'm leaving the 5x term on this side. I'll add a 2y to both sides. So effectively the -2y switches sides by changing its sign. The -10 is over here. On a test, this is perfectly satisfactory for me for standard form. For people who are really, really picky, like my math lab, they might very well insist that the variables be on the left. So some people require standard form to be like that. Some people are incredibly picky, and they insist that the coefficient of the x be positive. If you were to have a -7 here, you would have to multiply both sides of the equation by a -1 to change the sign on the x. But we're not going to worry about that here. If I can write this equation into standard form, so what I was given is equivalent to standard form, then it's linear. Now, the reason it's called linear is because the graph is a line. When they say plotting ordered pairs, they're saying plotting points. Well, a line is determined by 2 points. So if you plot any 2 points, then you can connect them and graph the line. There is no need to plot 5 points to graph a line. I'm often disappointed when I see students doing that on an exam because it indicates that they really don't understand that they're dealing with a line. So I'm only going to plot 2. The 2 easiest points to plot are often the intercepts. So I'm going to find the 2 intercepts and plot them. First, down here, I'll find the x-intercept. To do that, you set y equal to 0. So from the equation up above, -2 times 0 minus 10 equals 5x. Anything times 0 is 0, so I can ignore this term. So I can ignore it by covering it up. To solve what's left, I need to remove the 5 as a factor of x. To do that, I do the opposite operation. I divide by 5. So dividing this term by 5 makes an x. Dividing this term by 5 makes a -2. So the x-intercept is -2. I'll plot that point. Likewise, I can find the y-intercept. To do that, set x equal to 0. Well, I can use either of these equations that I want. We said that these were equivalent equations. That means that they have the same solutions. So if I don't like looking at this, I can look at this. So I'll go ahead and use the first equation, even though it will be one more step worth of work. So I'm setting x equal to 0. That means I leave y minus 10 equals 5 times 0. Well, that equals 0. To solve for y, I'll add a 10 to both sides. So remember, I'm adding 10 to 0, so I will get a positive 10 on the right, a negative 2y on the left. And then squishing down onto the very bottom row here, I can divide both sides by negative 2 to get rid of the factor that's on the y. And 10 divided by negative 2 makes a negative 5. So that's the y-intercept, negative 5. Those are the 2 points that I need. That defines everything I need to know about that line. I connect it with a ruler. When you're graphing lines, use a ruler. Use a ruler to draw your axes if you're not using, even if you draw your axes on graph paper, use a ruler. That way you have a uniform scale and your graphs will make more sense. When you graph a line, extend it off the bottom of the graph, off the top, or the sides, depending on whichever it is. You need to show that you understand that a line extends infinitely in both directions. That's what the arrowheads mean. So part B. Well, we look at this, and first off, we were supposed to decide whether this equation is a linear equation or not. Well, you can come at it 2 ways. First, you could try to get it into ax plus by equals c form, but to do that requires that somehow you get rid of the absolute values. And we saw in the previous section that the only way to get rid of absolute values is to trade them for 2 equations. So the absolute values would give us 2 equations. So this is not going to be possible. The other way you could do this, to answer the question, to determine that this is not a linear equation, is you could plot a few points. 3 looks like an interesting point. So I would ask myself, well, what happens if x equals 3? Then y equals 3 minus 3, absolute value, and that would be 0. So when x equals 3, there is a point on the x-axis, an x-intercept. Well, what happens if x equals 0? Then y equals 0 minus 3, which is a negative 3, and its absolute value is going to be 3. So I would have that point. Now, if I'm going to be linear, every point that I plot has to lie on the line through those 2 points. So I'll try another point. I will try, say, 5. And I find that I've got a value of y equals 2. So at 5, I have this. And those 3 points do not lie on the same straight line. So 3 points not on a line. Therefore, it's not linear. As long as you uh, avoid an unlucky guess. Sometimes you can have a nonlinear thing and graph 5 or 6 points, and they all lie along the line because you happen to pick the wrong ones. But in this case, it suffices to show that this is not linear. In fact, the graph of this function, I picked the 3 on purpose. The graph of any absolute value function is shaped like a V. This is the normal absolute value, y equals absolute value of x, shifted 3 units to the right. We'll learn later in the semester that that's what the minus 3 did. It shifted y equals absolute value of x 3 units right. The next problem is a bit of a story. We're able to describe a graph by using some words. This is a story of a trip. Each sentence tells one stage of the trip. So you read through the story, then down at the bottom you find what you're supposed to do. Represent his distance from home as a function of time in hours. So there's some special wording here that's very, very important to learn here. If you see the words as a function of, that means that you're supposed to write down a function. You're supposed to somehow capture the relationship between two variables. Every time you see as a function of, if you go back to the left, what you find immediately to the left is the output variable, the y. What appears immediately to the right is the input variable, the x. Now, you don't always call these x and y, especially in applied problems, but we're thinking about this being the x, the input. This is on the horizontal axis. The y's we're thinking of as output, and this is on the vertical axis. And in fact, in a problem like this, I might very well not use x and y as the name of the variables. Since I'm representing distance, I'm going to use a d because it's more mnemonic. And since I'm representing time, I'll call this variable t for time. Now, sometimes they tell you the units to use, and you've got to stick with the units that are specified. That's what they're requesting this graph be made like. Over here, they haven't specified any units. I did that on purpose because I wanted to let us off the hook about calculating the exact shape and slope of things on the graph. We can just kind of fudgelate things now. The distance might very well be in, say, miles, at least in this country. So this is an important vocabulary point. Whenever you see as a function of, this is exactly how you tear it apart. The y will be on this side, the x will be on this side. Now we get on with the story. We'll need some graph paper for this, so pull that up here. And I've gone ahead and labeled the graph paper the way we need it for the problem. Each of the ticks on the x-axis I'm letting represent 1 hour. I've labeled the axis with the variable, and when I have units, I put those on the axis in parentheses. This is part of communication. Be nice to your reader. Up on the y-axis, I've labeled that with a variable for the output. I'm using a d here, so officially it's the d-axis, and I'm just assuming that it's miles. I'm not going to bother labeling the d-axis with tick marks because they haven't given us in the problem any information about how far he travels each time. That's left purposefully vague. So we start with the story. Dale drove rapidly from his house for 1 hour. Well, we can assume that if D represents the distance from his house, Dale started at distance 0. His car started parked in the driveway, and he drove rapidly for an hour. Okay, so we will have him driving for an hour. That means that as he's driving, the distance increases. So here he's a certain amount of distance from the house, maybe 40 miles or 50 miles depending on traffic, but he has traveled for 1 hour. So we'll draw a graph up until we get time equals 1 hour. At this point, he discovers that he's left his suitcase at home. So at this moment, he has an oh my gosh moment. And that's right here on the graph. So he returned in 45 minutes. That means that instead of taking a full hour to get back, he takes 45 minutes. That's 3/4 of an hour. A half an hour would be here. 45 minutes would be here. So at an hour 45, he's back in the driveway. And his blood pressure is incredibly up. He immediately grabbed the suitcase and headed back, breaking the speed limit to make up for lost time. Okay, so we assume that he had been following the speed limit here. If he's breaking the speed limit, that means that for every hour of time he's making more distance, so the graph will be steeper. So we'll assume that his graph is something like this. Okay, so he's going to start doing that. And he's going to drive for 2.5 hours like that until the state police pull him over. So from an hour 45, there would be 1 hour, 2 hour, and then a half. So a little bit past 4 o'clock, the 4th hour out, he gets pulled over. This would be the point vertically above that. So he drives like this until he gets pulled over. So he's right here when they pull him over. Okay. The state police officer takes 30 minutes to write up the ticket. Well, if he's sitting on the side of the road for 30 minutes, that means his distance from the house is not changing. So for 30 minutes, from 15 after until 15 till, his distance is not changing. Then he took off, driving safely below the speed limit for another 2 hours. So he's going to take off from this point, but he's going to go for 2 hours. So there would be 1 more hour, there would be a 2nd hour. So somewhere up here, he's going to intersect. He's not going to be going this fast. He's going to slow down some. So we say he does that. So that's a graph of his trip. Now, we don't have any labels on the y-axis because we didn't have any distances in the problem. And that was just so that we didn't have to do any calculations. We could just tell this as a story.